So today is the day we leave our serial lives behind, because we've spent a lot of time talking about performance and how to get your serial code to perform, or how to use libraries that already have this performance optimization done for a single core. We've looked at how to use multiple cores by basically scheduling separate serial core jobs on the same multi-core node. Today we're going to actually try and use multiple cores working on the same problem rather than different problems, or rather than not using them at all. And there's kind of two ways that you can do this. It really is an architecture based decision. And so today we're going to talk about shared memory programming. Shared memory programming is programming a machine that has a lot of cores, but one memory, and all those cores can see the same memory. For that, they have to this sharing of this memory has to be somehow done, and the way it's done is the memory is in the same box as the cores. So when we talk about the GPC, we have different nodes. Each node has 16 gigabytes of memory and 8 cores. All those 8 cores can see all of that memory. But the different nodes have separate memory, and so you take two nodes, then the core of one node cannot see the memory of other node. So that's not shared memory, that's distributed memory. And we'll tackle that in a few next week. So today we're going to look at how you do shared memory programming. So this is the model. So imagine you have a big block of memory, and you have these 8 cores, and they all can see it. So each core can have something else to do. They can have their own instructions that they're executing. We will have control over that, but they basically can run their own program. And the way that now, if they have to tackle one big problem at the same time, that problem somehow is probably stored in memory, and all the coordination between these different cores happens through memory. So it's not that there is no communication here, it's just done through memory. Now, it'll turn out that you could also pretend that this is a distributed memory machine by just saying, well, I'll just assign a bit of memory to each of the cores, and I won't look at the other cores' memory. And so it is possible to do distributed memory programming on a shared memory machine, but it's not as efficient, because now, since I've divided up the memory, I will explicitly have to send a message from core 1 to core 2 if that's necessary, and copy things over, whereas the data is right there. So it's not as efficient as using pure shared memory program. Okay. So just to get a little bit used to the idea of threads of execution and other nomenclature, the memory is shared. It's one big shared memory. The cores are separate, and each core executes a thread of execution. This is basically a program on its own. Okay, so each has a program to run, and they might run it in any. They just independently from one another. And the way you program shared memory machines these days is almost always with a thing called OpenMP. It's a standard. It's basically a way to take C++, or Fortran code, and that is serial, and then add some things to it to say which parts can be done in parallel and how. So it's really nice because it is an incremental way of parallelizing. You take a serial code that works, and now you see, okay, there's parts of it that can be done independently by different cores. Let's just put a little note there, tell the compiler, this next part can be done in parallel, please do it. And then the compiler takes the work of starting these threads, assigning the work to different cores, making sure everything comes together at the end. So these nodes that we add are called compiler directives. And so that's what we'll look at, a directive-based way of programming in parallel. The standard is now at version 4, I think. You can find it on openmp.org. There's a lot of information on the website there, so it's worth checking out. If you're one of those people that like to read standards, start a few standards back, because the standard 4 is really, really long. Start with OpenMP 2. read that first before you, because it actually is readable. But that's if you're in the habit of reading standards. Okay, so this is what's going to happen when we parallelize. So you can imagine that we have our serial code to begin with. What do we do to make it parallel? And these are the steps you have to do. How you do it, we'll discuss next. So these directives all start with lines pound, pragma, OMP. As in C and C++ compilers, by convention, anything that starts with pound pragma is a preprocessor. It looks like a preprocessor thing. It's something that the compilers are allowed to skip over if they don't understand what follows. So it's something pragmatic, a pragmatic extension. Now this extension has been standardized by having a keyword OMP, which is short for OpenMP. So any line that starts with pragma OpenMP means it's an OpenMP notation. And that's what you do in the code. Then in addition, you have to tell the compiler you really want this stuff to work. So for G++, that means you have to add a flag to the compilation, -f OpenMP. Otherwise, it will actually skip over those lines. You have to do the same actually for linking. So again, with linking, you have to say, okay, this isn't an OpenMP application. It needs to be able to do threads and spawn them and set. So that's what's different with compiling. And when running, you could run it now, and it will take it will use some amount of cores or the threads. You can control this by setting an environment variable called OMP num threads. By default, it'll probably take as many cores as your machine has, but maybe that's not what you want. So you can actually control and set this to, say, 8 for the GPC nodes and get 8 threads. If you want to follow along, or if you want to later check some of the examples that are in here, you could clone this this directory on Cynet and go to OMP and get the examples here. So here's a very simple example of what this looks like. If you imagine that there was no pragma OMP parallel, this would just print out some things. It will print something at the start of the program. It'll write out hello world from thread, and then there's some function call, and that's it. So if I compile this, I have to do my C++ 11 like we've always done in this course, and here's my C. And then here's the extra flag -f OpenMP to make sure that it recognizes this this pragma. Now if I run it, if I set the number of threads to 1 and I run OMP world, I just get at start of program and hello world from thread 0. But if I set the number of threads to 8, I get hello world from a bunch of threads. There's the code here still. Yeah, here's the code again. So the single thread is somewhat easy to understand as long as you realize that the threads are numbered from 0. So at start of program is printed, there's only one thread, and it prints 0. At 8, somehow I now have 8 threads, and they have different numbers. Now you should note right away that I'm actually seeing these messages from the different threads in sort of a random order. In fact, if I run it again, the order is probably different. What do you think that is? Something wrong? Did we make a mistake? Is the compiler broken? That's right. That's right. So, was that your guess too? Yeah. So they run in parallel, and they have an order in them because they have a number, but that doesn't mean that it runs in order. It runs in parallel. So whoever happens to be done with converting this thing to a string just before the other person, before the other thread, will get its output first. Now, theoretically, they should all take exactly the same time, but they all there's fractions of seconds, of nanoseconds difference, which is enough for the order to be non-deterministic. It's something you have to get used to when you're doing parallel programming. In parallel programming, the whole thing is finding concurrency, finding things that can be done at the same time. If they can be done at the same time, it means their order doesn't matter, which means if you start printing out things, their order will be different. This can be a little bit annoying if you're doing unit tests, because if you test it for the output of this and it's different every time, that's difficult. So you need to be aware of that, but you shouldn't be disturbed by it. It's just, yeah, it didn't matter what order it is in. Well, then you get it in any order. So OpenMP has these pragma extensions to the language, but it also has a library with a couple of functions. Here's a few of them. Some of them seem very useful, like I want to know how many threads are running. I want to know what my current threads number is. I might want to set the number of threads, maybe dynamically in my program. I don't want to always have the maximum number of threads. Maybe there's a reason for that. And I might want to get the number of processors actually on the node. So there can be a difference between the number of threads and the number of processes, because I can set this environment variable. So I have access to that through the library. And because it's a library, I need to include a header file for it so that these functions are known. But I don't have to include anything to have the pragmas work. That's a compiler extension. So here are some of these functions. I get the number of threads and number of threads. So let's see what happens when I do this. So I have the same code as before. I have this OpenMP parallel where apparently I have 8 threads. And then there's another command or another statement here that tries to print the number of threads. And what's funny though is that the output is gone, but the output would be that it says there were 1 threads. This isn't the case where I still had 8 sets to the OpenMP number threads. So something funny happened here. This promise of OpenMP get num threads seems to be broken. And the reason is that we're not in parallel region anymore. So what happens in this little code is actually quite a lot. It seems to be very short, but let's go line by line and see what it really does. And you'll see why we have 1 thread at the end. So I'm including my IO, I'm including OMP.h to get the functions, string, which is where the toString comes from. I'm writing at start of program. So when I start my program, you saw it only prints that once. Apparently I start in serial. So when I start an OpenMP program, it starts in a serial mode, or as I call it, a serial region. There's only 1 thread active when I start my int main. The other threads do not even exist yet. Okay, even though I have set my OpenMP num threads, that's just for later. Right now I have 1 thread. I don't get more than 1 thread until I hit this pragma OpenMP parallel section. And so what it acts on is it actually takes the next block or the next statement and says, I'm going to do that in parallel. And so as soon as I hit this, it's going to say, okay, here's a block of code that you want in parallel. And what it does is it just now creates the 8 threads that weren't there before and has every one of these threads run the block of code or the line of code. So at this moment, 8 threads are spawned and are given this task to do, which is writing out hello world from thread. So each task separately asks for its thread number, and it gets somewhere between 0 and 7, and prints it out. And then that's it. That's the only statement that is covered by this block. If I want more statements, I have to put them in curly braces. So this statement here is past that parallel block, and it's basically back to the serial case. So what happens is that those threads that were spawned here for this one statement are closed off again. They're joined, as it is called. And so all those 8 threads join again into one single thread that just prints out how many threads there are. But if all the threads are joined, if there's only 1 thread, then the correct answer of OpenMP get num threads is 1, because there's only 1 thread at that Okay, so that's the model of OpenMP. You start serial, you hit a pragma OMP parallel, you spawn your threads, you do whatever is in that block, and the threads get closed again, and you're back into a serial. Okay. So suppose I do want to know how many threads there were. Well, I have to ask that then when the threads were there. So here's a case where we can do that by basically storing the value of the number of threads in a variable and then printing it out afterwards. So I'm rescuing my value here. So let's go over this slowly too, make sure that we understand what happens here. We have two variables, t and n threads. T here gets assigned the thread number, and then just because I want to be efficient, although it doesn't really matter, I only want one of the threads to ask for the number of threads. So there's 8 threads available here. They're all running at the same time because I'm in this pragma OMP parallel region, but only one of them needs to ask how many threads there are. The other ones could also ask it, but they would all get the same number anyway. So whenever there's a case where you want to pick out one particular thread among all of the threads, you always pick thread 0. There's something very special about thread 0. You have an idea why we do thread 0, why it's so special. Right? When it's serial, it will be thread 0. That's right. Yeah. You would think so, but the real reason it's just 0 is that no matter how many threads I have, I always have a thread 0. Right? If I said I want thread 7 to do it, and now I'd run it with 4 threads, it doesn't get done. So if I want it done by somebody, I will have to have it done by 0. It actually turns out that formally it is not necessary that thread 0 is also the master thread that was accessible outside. So they could be different. It all depends on the compiler and the particular implementation. But there is always such a thread 0, and so that's nice. So that's why we do 0. We store it in a variable and we print it after. The variable doesn't change, but it doesn't change for a good reason. But it doesn't change once we exit this parallel block, and then we print it, and we'll get 8. So here it is again. So we run it. It launches the threads, and there's a couple of things that we now have to worry about because we're using variables, and as strange as it might seem, when you use variables on a shared memory programming model, you suddenly have to worry about whether they are shared or not. So there's these extra statements that you have to tell or have to specify with the pragma OMP. This slashes is a continuing of the line to tell you what these variables are supposed to be like inside the parallel region. So I have 2 variables that exist outside. And there's basically 2 things that can happen. I have an n thread and I have a t. Whenever I spawn my cores, I might want, or my threads, I might want each thread to have its own copy of that variable, or I want them all to access the same variable. Now the latter seems more natural in a shared memory context, right? You take a shared memory machine, of course everything is shared. I have 8 threads, well they are all going to see the same n threads and the same t. But this becomes a little annoying if each thread has to do something different with t. So in this case, for instance, t gets assigned the number of the thread, right? So that is different for every thread. If I had this t be a single variable, a single shared variable, then these 8 threads all start pushing their own number into this poor little variable. And who knows what actually ends up in that box. So each thread has to be able to have some private memory for it to do something different. If each thread is supposed to do something different, they have to have some variables of their own. And so those are the private variables. So t has to be private for it to be possible for every thread to store its own value of t. Right? So that's the case with t. On the other hand, the number of threads is something that should be the same for all of them. So I really want that to be a shared variable, and I want, and so that when I set this for thread 0, all the threads would see the same value of n threads. This is an important point when you're dealing with variables. There are really two classes. There's a few extra subclasses, but those are the two main classes. Yeah. Yeah, so that's a good question. And so the answer is, because a decision had to be made. What happens to these private variables when I exit? They get destroyed. That's the default. So when you have a private variable, when they get in here, basically what happens, I think I'm getting 8 copies of t, but I'm actually not. I'm getting 8 integers that aren't even a copy of t. They're just separate integers. So I don't know what the initial value is, which doesn't matter here. And then likewise, when I get out of the region, those 8 extra integers are just discarded. They're not used anymore. That's a good question, and that's because this example works both in C, Fortran, and C++. Well, not literally in Fortran, but in C and Fortran, you have to do it this way, or you used to have to. C is a little bit advanced now, but yeah, we can define a variable inside, and then it becomes private automatically. We'll see that in a second. But it still means there's 2 classes of variables. There's the private ones and the shared ones. So in this way, I explicitly state which one is private and which one is. Yeah. Yeah. It will have absolutely nothing to do with it. Yeah. Yeah. So it's very private. There are some ways to copy in and copy out, but usually there are exception cases. But the standard thing is it's private. Even if it was not like that, it's first have to create these 8 integers and then copy it in anyway. So that's why the default is not to copy in. That is an extra operation you might not need. Okay. Yes. So the default none I put in here because there's actually defaults in the standard that says that certain type of variables become shared and others become private. So if I don't say anything, I don't say default none, I don't say private, I don't shared, the compiler will make something up that might seem reasonable. The trouble with those reasonable defaults is that they're reasonable 50% of the time. And so you don't really want to use the defaults. And to force the compiler not to use any defaults, there's a default none. So what default none does, it says, compiler, I don't care what you say or what you think. I'm going to tell you exactly who is shared and who is not. Yes, so you could do default private or default shared, and everything would become private and become shared. The trouble is if you make a default, you're going to at some point add a variable that shouldn't be that, and you forget to define it. So especially it's sort of good practice to be specific when you're developing your code and say, I don't want to spend time later debugging and figuring out which ones of my variables are private and shared, whereas I could have just told the compiler. Because when you're writing your program, like you'll be able to figure out quite easily which of the 2 classes you want. You want it private? Does every thread need to do something separate with this variable? Or do you want it shared? Are they working together on this variable? And you will know that when you're writing it. But if you don't specify it because the defaults make that happen automatically anyway, you come back to your code a week later and go, it's not working. But now I'm not quite sure if my variables, what I intended my variables to be. Was n thread supposed to be shared or not? This is just a way of sort of documenting and making sure things behave exactly as you think it is. Yeah.
So, say something.
Exactly. So what will happen, and that's another reason why default none is nice. If I now use that variable here and I didn't declare it shared or private, the compiler will say, hey, I don't know what to do with this one. which is a good hint because, okay, I either make sure it does what it is, or maybe I was using something I wasn't intending. So only the ones that are specified are now accessible in place. Now, as a last remark on this little piece of code is that I must make sure that nthreads is shared, because if it was private, it would be destroyed after, right? So you could say, okay, I could make nthreads private because it's just set by one thread, but then it will be destroyed afterwards. And there's no way to say, oh, give me back the variable that thread 0 had that was called t, or nthreads. There's no back grabbing. They're gone after that. Yeah. Pointers are funny because this is more of a, it's a language thing. So it says, okay, these variables exist, and they are either private or shared, and if they're private, I make new copies. So if you did it with a pointer, something funny happens, because usually a pointer used to make an array, right? So if you make a private, if you make the pointer private, you would think that you get that array 8 times, but you don't. You get 8 pointers without allocated memory. So you want to be very careful with that. And if you need, so yeah, you want to be very careful with that. If you make a private pointer, you just get 8 copies, not even copies, 8 values of the pointer, and they don't have that memory. If it's shared, it doesn't really matter because it's just pointing at the same. There's 2 ways. You could do it inside, or you could make it, if you use a class that has that when you copy a class, it creates a new copy, then that will work. So private works with classes that array. So if you have a std vector or an R array, which R array does something funny, but if you have a vector or a class that reallocates memory when you copy, then that will happen. Yeah. Okay, let's go on. So here's the trick you kind of alluded to before. Since this is C++, I don't have to define my variable int t here. I can do it inside, because that's the only place I need it. And when I do that, it automatically becomes private, because every thread is executing this code, and every thread sees this statement, which basically means set aside some memory for a variable t. So if each thread does it separately, they get different variables, different bits of memory. Okay. So it's nice because now I don't have to specify that they are private anymore. Right. So we actually did the like half of the essence of OpenMP right now already. Spawning threads and variables. So let's just look at some more convenient things to do, because we singled out thread number 0 to get us the number of threads, because thread 0 always exists. That was our reason. But really, we do not care which of the threads is going to ask for the number of threads, right, in that code. Anyone will do it as long as only one does it, because that's so. There's a construction or a keyword for that in OpenMP called pragma OMP single, that, like pragma OMP parallel, takes the next line of code or the next block of code and makes sure that it only gets executed by one core. And then really what happens is whichever thread is ready to do something again, it's kind of like a scheduling, will get to do that one construction. So I have my OpenMP parallel region. This spawns my 8 threads. And then in that region, so the region now extends to the next real line of code, not those fake ones, the real line of code. In that region, I say this command here, although in a parallel region, will only be done by one thread. Yes?
With the first line single.
Yes, yes, you can do that. So it can be very useful, for instance, to print out like what time step you're in, because you don't want this from every thread. But yeah. Makes sense. So now we've gotten rid of the if statement. It's shorter code. One thing to always check for after is to see if this code would still work in serial. So what if I take out these lines of code, and it kind of looks very similar, right? Okay. How many threads do I have? Well, I should say one because I only have a serial code. So ideally, in OpenMP programming, the code that you have starts off working as a serial code. You add some things to make it parallel, but if you took those things away, ideally the code would work just fine again. It would just basically be your serial code again. Yeah? Good question. Yes. So the point where the threads join is really called that way because they are waiting for one another. So if say thread 1 gets to do this and the other ones and is done and the other ones are stalling for some reason, it waits for all 8 of them to be at that spot. So whenever you have an OMP parallel block, it's blocking at the end. It's waiting for all of them to be there. And so it's something to be aware of when you're doing like your performance tuning. You don't want to open a parallel block and close it, open and close it. If you can, you want everything to be in parallel. But it's usually a consideration further down the road. Okay, so that's spawning threads. But they were all doing the same thing, right? They were saying who they are, and that's it. What we really want to use these multiple cores for is to divide up work. We have a bunch of work to do, and if all of the processes did the same work, we're not getting any speed up. They're just all doing it. That's great, but it doesn't help us. And so one way in which we get typically bunches of lots of work is when we have a loop over an array, and that's kind of the workhorse of a lot of scientific computing. I have a lot of data or a big array, and I need to do something for every element in the array. So here's a loop. It doesn't make any sense because I'm only showing the syntax now. We'll see something that makes more sense in a little while. Here's a loop that is in a parallel region. I've said what I want to happen with my variables. And inside the loop, I have a loop from 0 to 15 that prints out what thread I am. We've got it here in this variable t again. And it says what value of I it is. So if I run this with two threads, what do you think the output would be? How many lines do I get? Note that this is one line, right? How many lines do I get if I run with? 32, right? Because they're all doing the same thing, right? That was the whole point. I have 2 threads. All of them get this piece of code to do. So that still doesn't help us. Here it is. Still doesn't help us. In any case, we want to divide up this loop. So that's what we want to do. We want to do what's called workshare, some work sharing. We want this loop to be divided up amongst the different threads. And so that is so common that's a standard construct in OpenMP. So you take your loop, and you can imagine what you might want to happen. You have 2 threads, you have 16 things to do. Each thread should get 8 things to do, and just do them in parallel, right? And that should then be twice as fast, because each of them is only doing half of the work. So to do that dividing up, you just put pragma OMP4 in front of your for loop. So you have a for loop that has 16 iterations. You put pragma OMP4 in front of it, and it divides it up in 2. If you had 4 threads, it divides it up in 4. If you had 8 threads, it divides up. So it does the division for you. It's very nice. It's very simple. And when you put that in, and we have 2 threads, we basically get a division of labor. The different i's gets assigned to different threads. Now, the output here is a little bit hard to read because the order of printing is still random. But if you look at everything that thread 0 gets, 0, 0, 0 gets 0, 1, 2, 3, 4, 5, 6, 7. You see it gets a contiguous block, and that's the default. So it could do this work sharing in many different ways, but the default is you have 8 threads, you have an iteration space from 0 to n. It takes n over 8 for the first, the next n over 8 for the next thread, etc. If you had 8 threads. Okay? So it's a very easy way to break up the work. There's more advanced ways to do it, where you specify exactly what task goes to a core. We're not going to talk about that, but there's fine-grained control if you need it. But for a general loop, that's typically not what you need. So here's a little example of how to use that in a slightly more realistic way. Once again, I am violating our own principles by showing you how to implement a DAXP routine, which is in BLAS, and which you should never implement yourself, because there's already a BLAS implementation that is faster than you will write it, or at least it is your first try. But I'm going to do it anyway, because the DAXP, which was ax plus y, right? So in a vector, is very parallelizable, a single loop. So since I want to show how to parallelize a loop, this is a useful case to look at. So what happens in this piece of code is that I have an array of 10 million doubles, or I have 3 of those arrays. I initialize them in some function init, so those 2 arrays will get something put into them. Then I call DAXP, which I've defined here in terms of R arrays, which is kind of useful because that way it will never conflict with the BLAS routines. But it will do a times x plus y and put it in z. And then it will time how long it takes. And so here's my little init. Init just puts I squared and I plus 1 squared in x and y. It's a nonsense fill, but you want something non-trivial in there. And then the DAXP is just zi equals a times xi plus yi. So here's my loop. This is I don't really care about the init, although the same principles apply. But I want to parallelize this loop. So right now it's a serial code. It will work. It will give me an answer. What should I do to parallelize this? Using OpenMP. Where's the concurrency? What can be done at the same time? That should be our question, right? Yeah. Yeah, right. There's no this. If I did this in any order or at the same time, that would give the same result because every I is separate. Right? If there was any cross I communication, it might be different if there was a data dependency, but we don't have that. So this is the thing always to look at for when you're parallelizing. The syntax is one thing, but you have to see where the concurrency is. You have to see if the loop iterations are independent and can be done in any order and independently of one another. If that's the case, it can be done in parallel. Only then can you say, okay, I have stuff that can be done in parallel. Now I'm going to divide the work over threads. So I have to know in my little piece of code here what to do with the variables. There's some variables in here, and so I can put my pragma OMP parallel in there and the pragma OMP 4, but I have to make sure that my loop variables make sense. Or sorry, my variables inside that loop are properly shared or private depending on the context. So here's my pragma OMP parallel. Here's my pragma OMP 4. It's not strictly necessary to have the curly braces here, but I just put it for clarity. And I've specified what is shared and what's not. Now, each thread is doing something different, right? So you could think that they don't really need to share anything. They're working on their own separate piece of the code, but they need to have access to the same data that was already in memory. You don't want to make a copy if you don't. It's already in shared memory. So you're just going to make, in this case, pretty much everything is shared. The x, y, a, and z, as well as n, are all shared. But there is a private variable here. Can you guys see what the private variable is? I, exactly. It's private because it's locally defined, but it's private because it has to be. Every thread will have a different range of I values. So thread 0, say there are, say n is 16, and I have 4 threads, then I, for thread 0, will go from 0 to 3. The next thread, it will go from 4 to 7. But it has to be able to have those values at the same time. So I is sometimes 3 and 7 at the same time. The only way that works is if each thread has its own private function. So it happens automatically here because we are defining the int inside. If I had done it outside, I would have to say private I. Okay. Everything shared, or this makes sense? So syntactically, this is very easy. It's even easier if I take out the shared and the default none. But you're putting yourself at risk. But it's only easy because I've already verified that there's no data dependencies, and I made sure that all my variables are correct. If there's any data dependency here, what will happen is that my result will basically just be wrong. Yeah.
I was just curious to how you. It feels like you're running over the same instances, but you actually want to run over different instances.
Exactly. Yes. Right. So yeah. Okay. So this is the magic that happens. That is done for you by OpenMP. So what happens behind the scenes is, okay, OpenMP sees your loop. It says I ranges from 0 to n, and it basically replaces that. Say you had 4 threads by 4 different loops that have different ranges. It computes what the starting I is for each of those and the end I, and it writes a new loop for you, and it gives only which runs over a subset of I, and it gives that loop to one of the threads. So it seems like they're all doing the same thing, but the Pragma OMP4 is basically changing your code, right? And the reason you do it this way is that if I take out the OMP4s and the OMP parallel, it is the same code as it was in serial. So it's a nice way to do it, but it is actually doing a lot of work for you, right? Yeah. This also means that there might be very complicated loops that you write where the exit condition is special, that it won't be able to figure out what's going on. If it can't tell how many elements are in your loop, then it won't be able to divide it up, which makes sense. But so then it's time for a different approach. It'll do it as evenly as it can. Yes. Yeah. Just as for more convenience. So one thing that's convenient is if we define our integers that are private or our variables that are private inside the block. Another thing that's very convenient is that constants are always automatically shared. So I'll show what that means in a second. And another convenient thing is that you often have this parallel and Pragma OMP4 following each other right next to each other. There's a Pragma OMP parallel 4, which just means it's both of them. So that means that the code actually, instead of looking like this, I'll do this. So I make constants here and here, which means that I now don't have to specify them in shared anymore. So constants aren't really treated as variables anymore, they're just constant. The reason that doesn't negate the idea of having default none is that because it's const, I can see what it is, right? Regular variables that aren't const, I can't see whether they're private or shared unless I tell them. But const, always shared. You're not changing this variable anyway. It doesn't really matter. If I copied it in, it'd be the same as not copying it in, so you might as well use them as shared. So that's kind of convenient because you don't have to worry about those constants. And then this combination of OMP parallel and OMP4 just becomes OMP parallel 4. You do all your defaults and you share it, and that's it. So once you get a little bit used to this, or if you look at a master OpenMP programmer, it'll seem like magic. He takes your code, he puts like 3 lines in there, 3 pragmas, and now it runs 8 times faster, and you go, wow, right? But a lot of things are happening, right? That's just, it's convenient, but the parallel and is a different thing from the for, is a different thing from making sure. So there's yeah, so it might be brief and might seem simple, but it isn't simple. You have to know exactly what you're doing for this to work. If any of these assumptions are that these can be shared, that this can be done in parallel, that this is a for loop that should be divided, that can be divided. If any of these assumptions are wrong, this simple addition of one line isn't going to make your code either faster or correct. Okay. So once we've put that in, it really looks like, oh, I just add that and I just add that, and it's simple and it's now in parallel and it's 8 times faster. Anyway, let's check that. So the same code that I pointed to at the beginning has the DexP in it, so you can make DexP and a parallel version of it. And then I ran it with 8 cores, and it was faster, so that's good. It was only 5 times faster. It's weird, right? Any ideas why only 5 times? No? You think so, but that's right. So that is one, absolutely. That could. There's overhead. So the way you would test whether it's the overhead part, or the way I would do this, I just make n larger, because the larger n is, the less, relatively speaking, the overhead would be. So I can test that. Yes. There's a serial part, but it's pretty small. So again, let's go to the driver routine. Where was it? Here. It's basically this allocation part, right? So that is almost a constant cost too. So again, I should be able to improve my scaling with n, my scaling with the number of cores by making a bigger problem, which is typically a nice way to go about it. It's this strong scaling a weak scaling idea where if I make my problem big enough, it will parallelize perfectly. It turns out there's some leftover stuff that even if I make a really large array where the overhead can be neglected and the serial part is also negligible, I still get only 5 times faster. So we'll finish here, but that we'll see why and what we may or may not be able to do about it in the next class. But it has something to do with hitting another bottleneck. So this was a very simple case. Everything was independent. It was a loop. We put our own pragmas in there, and it didn't give us 8 times speed up. And it's something you should get used to. Whenever you parallelize a program, how it scales isn't necessarily exactly what you think is going to happen. Especially with OpenMP, the things like overhead or the fact that there are serial parts will mean that you don't get that perfect speed up that you might expect. And so, it's a word of caution when you're starting with OpenMP. Don't expect tremendous speed ups the first time you put in these pragmas. Okay, we'll look at more performance OpenMP